All right, in today's lesson, we're going to compare the effect of changing dimensions on the surface area and volume of similar solids. So let's go back for just a second and talk about our scale factor. As you remember, the scale factor is the ratio between corresponding parts of similar figures. In this case, it's similar solids. So we're going to draw a cube. And drawing cubes is pretty easy. It's even easier with our isometric dot paper. So we've drawn a cube that's twice as big as the other one. So this one has a side length of 2, and this larger one has a side length of 4. So let's compare the ratio of the side lengths. Now, corresponding parts can be anything. It could be length, width, circumference, perimeter, any corresponding part. And for a cube, there's only one part, the length of the side. It's all the same. So all the sides in this first cube are 2, all of them are 4, and the second one. So what's the ratio of the side length of the small to the length of the large cube? Well, it's simply 2 compared to 4. And that's the same thing when you reduce it as 1/2. So now we're going to compare the surface areas and the volumes and see what happens. So for the small cube, the surface area, each side has a surface area of 2 times 2. It's just a square, 2 times 2. Well, how many sides does it have? Well, you might remember a dice has 6 sides, and it is a cube. So each cube has 6 sides. So we've got to multiply the area of each side by 6. And so that's 24. So what's the surface area of the large cube? Well, that's 4 times 4, and you've got 6 sides, and that's equal to 96. Well, what about our volumes? Well, the volume of the small cube is simply 2 cubed. That's 2 times 2 times 2, and that's equal to 8 cubic units. What about the large cube? Well, the volume of the large cube is 4 cubed, and that's 4 times 4 times 4, and that's 64. All right, well, what's the next step? What's the ratio of the total surface area of the small cube to the surface area of the large cube? Well, we've already calculated that. The small cube, it's 24. The large cube, it's 96. And that reduces to a fraction of 1/4. All right. Well, now let's look at the ratio of the volumes of the small cube to the volume of the large cube. Well, the small cube has a volume of 8. The large cube has a volume of 64. And that reduces to a fraction of 1/8. Well, that's interesting. So now let's compare the ratio of the side lengths to the ratio of the surface area. What do you notice? Well, the ratio of the side lengths is 1/2. That's the ratio. That's our scale factor. Well, if you square that, you get 1/4. So that's interesting. Now, you might remember that from our earlier lesson when we talked about the effect on area of scale factor when you changed it. And that's exactly what we found, so that's what we would expect. So whatever the scale factor is, you square it to get the ratio of the areas. So the ratio of the areas, the surface areas, is the square of the ratio of the lengths of the side lengths. So now let's compare the ratio of the side lengths to the ratio of the volumes. What do we notice? Well, the side lengths is still 1/2, and the ratio of the volumes is 1:8. Well, the way you get that is you cube it. So now we're not squaring it anymore, we're cubing it. So 1/2 times 1/2 times 1/2 equals 1/8. So now we have the ratio of the volumes will be the cube of the ratio of the side lengths. Okay, so if we go back to our original, we get the ratio of the side lengths, that's 1/2, and you notice that's our scale factor, and we will square it to get the ratio of the surface areas. And then we take that same 1/2 and we will cube it to get the ratio of the volumes of the two cubes. So what does that mean? Well, 8 of these smaller green cubes will fit inside of one of these large cubes. So it's a very interesting conclusion. It's maybe different than what you expect. You doubled the size, but you have 8 times the volume. Now we're going to do some examples. We're going to use the information that we just went over to solve some problems. First example, what would the effect be on the surface area and volume of a pyramid if I triple the dimensions of a pyramid? And we're talking about tripling all the dimensions. So that's our scale factor, right? Our scale factor for corresponding parts is 3. Well, we're talking about the effect on the surface area. So we're talking about an area compared to the scale factor. So it's going to be the scale factor squared. So that's just going to be 3 squared equals 9. So our effect on the surface area is the surface area will be 9 times as large. What about the volume? The volume will be the cube of the scale factor. So that will just be 3 cubed. So the volume will be 27 times as large. So it doesn't matter what the numbers are, that's true for all of them. If you triple the dimensions, no matter what they are, the volume will be 27 times as large. All right, one more quick example. What would the effect be on the surface area and volume of a cone if you cut the dimensions in half? All right, so now the corresponding parts, or our scale factor, will be 1 compared to 2. And it's the same thing, surface area and volume. So the surface area will be our scale factor squared, and that's just 1/4. So the surface area will be 1/4. What about the volume? Well, the volume will be 1/2 cubed, and that's 1/8. So the volume of the second cone will now be 1/8 of the original. All right, a couple more. Here's our third example. 2 similar cones have a radii. Radii is plural of radius, like that. I like that plural. Radii of 10 millimeters and 15 millimeters. All right, we're talking about dimensions. We're talking about corresponding parts. So we know what the scale factor is. Our scale factor is 10 over 15. And that reduces to 2/3. So we know the scale factor. So So what is the ratio of the surface area of the small cone to the surface area of the large cone? Well, that's going to be our scale factor squared because it's an area. So 2/3 squared equals 4/9. Okay, we have two more problems. The containers of the right are similar cylinders. Find the height h of the smaller container. So we have the height of the larger container and we have the volumes of both containers. So once we know the volumes, we can compare the ratio of the volumes. The ratio of the volumes is 640 pi to 270 pi. Now, because we're comparing volumes, that's going to be our scale factor cubed. It's going to be the cube of whatever the ratio of the dimensions is. So we have our scale factor cubed. Okay, the first thing we want to do is reduce that if we can. So 640 pi, well, we have that in the numerator and the denominator, so we can cross that out, and we can also cross the 0 out. So we reduce that to 64/27. And that's our scale factor cubed. Well, to get our scale factor, we're going to have to take the cube root of that. So our scale factor is the cube root of 64/27. All right, well, let's factor these real quick, and we'll find that 64 is 4 times 4 times 4, and 27 is 3 times 3 times 3. Well, that's a pretty convenient number, and when we take that cube root, it just comes out to 4/3. And that's our scale factor. So now we can use that to set up a quick proportion to find the height of the smaller cylinder. So the large cylinder compared to the small cylinder, the height is going to be 10. 10 is the large cylinder, so it goes with the large side, over x. This is what we don't know. So let's cross multiply, and we'll have 4x equals 30. X is our height, and so height equals 7.5 inches. Our final problem. A regulation volleyball has a circumference of 66 centimeters. The ratio of the surface area of that ball to the surface area of a children's ball is approximately 1.6 to 1. So we have a ratio of the surface areas. Our ratio of surface areas is equal to 1.6/1. Now we're comparing areas, so anytime you compare areas, you're looking at our scale factor squared. We're trying to find the circumference of the children's ball, so we're going to need to find our scale factor. So the way we can find that scale factor is take the square root. So our scale factor is going to be equal to the square root of 1.6/1. All right, can we reduce that any? Well, not really. That's the same thing as the square root of 1.6 over the square root of 1, which is still 1. So that's another way to write that, and that'll make it easier when we stick it into our proportion. So what's our proportion look like? Okay, the ratio of any dimension, including the circumferences, it's equal to the square root of 1.6 over 1. And that's going to be equal to, this is our large side, the square root of 1.6 is larger than 1. That's going to be 66. In our unknown, what we're trying to solve for, we'll call x. That's the circumference of the small ball. So all we have to do is cross multiply again. We have the square root of 1.6 times x equals 66. And 1.6, the square root of 1.6 is about equal to 1.265. So x equals 66 divided by 1.265, and that is approximately 52 centimeters. So now we have the circumference of the children's ball, and good luck on your homework.